We will now turn our attention to nonhomogeneous linear systems. There are two methods to solve nonhomogeneous. The first is undetermined coefficients. The second is variation of parameters. In order to use undetermined coefficients to solve the system x prime equals ax plus f, all of the entries in A must be constant. And for F, all of the entries must have or must be constant, polynomial, exponential, sine, or cosine, or any finite sum and product of these, so any linear combination of these. Just like when we studied nonhomogeneous linear differential equations. So let's take a look at the system. X prime is equal to -1, 2, -1, 1, x plus -8, 3. So the first thing we have to do is we have to find the general solution, the complementary function. So we need the determinant of lambda I minus a. So this is the determinant of lambda plus 1, -2, 1, and lambda minus 1, which has determinant lambda squared plus 1. And so we get lambda is either I or lambda is -I. Let's take a look at lambda equals I. We'll get the matrix I plus 1, -2, 1, and I minus 1, which will reduce so x1 is equal to 1 minus I, x2. x2 can be any number, so our eigenvector is 1 minus I, 1, which means our solution vector, which is 1, 1 plus -1, 0, I. So the complementary vector will be C1 times 1, 1 cosine of t minus -1, 0 sine of t plus C2 times -1, 0 cosine of t plus 1, 1 sine of t. And so we'll get C1 times cosine of t plus sine of t, cosine t, plus C2 times sine t minus cosine t and sine t. Now we have to find our particular. So to find the particular solution, take note that f of t is negative 8, 3. So the particular solution vector is going to have the form a1, b1. And so the particular derivative of the particular is, of course, 0, 0. Now plug these in to the system. So 0, 0 has to equal negative 1, 2, negative 1, 1 times a1, b1 plus negative 8, 3. If we multiply this out, we'll have negative a1 plus 2b1, negative a1 plus b1 plus negative 8, 3. Now, of course, add those two now together. Negative a1 plus 2b1 minus 8, and then negative a1 plus b1 plus 3. And that whole thing has to equal 0, 0. So we get the system negative a1 plus 2, b1 minus 8 is 0. And negative a1 plus b1 plus 3 is equal to 0. Rewrite the system. Negative a1 plus 2b1 is equal to 8. Negative a1 plus b1 is equal to 3, negative 3. Solve this system, and we find that a1 has to be 14 and b1 has to be 11. So the particular solution is 14, 11. So we can now write out our general solution. Phi is the complementary plus the particular. And so here's our general solution. So let's now look at the system. X prime is equal to 6, 1, 4, 3, x plus 6t negative 10t plus 4. So we need determinant of lambda I minus a. Oops. So determinant lambda minus 6, negative 1, negative 4, lambda minus 3, which is lambda squared minus 9 lambda plus 14. So our eigenvalues are 2 and 7. For lambda equals 2, negative 4, negative 1, negative 4, negative 1, row reduces. So x1 and x2 are the same. So the first eigenvector we'll take as 1, 1. And so our first solution vector we'll take as 1, 1, e to the 2t. For lambda equals 7, we get 1, negative 1, negative 4, 4. This row reduces to 1, minus 1, 0, 0, which is the exact same as up here, which means we're going to get the exact same eigenvector. So phi 2 will be 1, 1, e to the 7t. So the complementary function, c1 times 1, 1, e to the 2t, plus c2 times 1, 1, e to the 7t. To find the particular, take note that f was equal to 6t negative 10t plus 4. So our particular will have the form of a1t plus b1, plus a2, and then b1t plus b2. Derivative would then be a1, b1. Plug everything in. a1, b1 is equal to 6, 1, 4, 3 times a1t plus a2, b1t plus b2, plus 6t negative 10t plus 4. This will give the solution, this will equal 6a1t plus 6a2 plus b1t plus b2 plus 6t, 4a1t plus 4a2 plus 3b1t plus 3b2 minus 10t plus 4. Now, since a1 has to equal this, we can write 6a1 plus b1 plus 6 times t plus 6a2 plus b2 minus a1 is equal to 0. And also 4a1 plus 3b1 minus 10t plus 4a2 plus 3b2 minus b1 plus 4 is also equal to 0. From here, we can write two systems. 6a1 plus b1 plus 6 is equal to 0. 4a1 plus 3b1 minus 10 is equal to 0. So this system comes from coefficient comparison of the t's, which means the second system will come from the constants. 6a2 plus b2 minus a1 has to be 0, and then 4a2 plus 3b2 minus b1 plus 4 is equal to 0. We have to solve this system first. This system will give us solutions for a1 and b1. We can then replace a1 and b1 over here. Then this is a system of 2 and 2 unknowns. Then we can solve this for a2 and b2. Solving this for a1 and b1, we'll get that a1 is negative 2, b1 is 6. This system would then become 6a2 plus b2 plus 2 is equal to 0. 4a2 plus 3b2 minus 6 plus 4 minus 2 is equal to 0. We can now solve this system for a2 and b2, and we get that a2 is negative 4/7 and b2 is 10/7. Our particular solution would then be of the form negative 2t minus 4/7, 6t plus 10/7, which can be written as negative 2, 6t plus negative 4/7, 10/7. Therefore, need to make a correction. If we come up here, this was supposed to RREF. I'm sorry, that was the wrong one. For the lambda equals 2, the matrix was supposed to RREF to 1 1/4, 0, 0, which makes this negative 1/4 x2, which changes this, our eigenvector, to 1, negative 4. And so our first solution would become 1, negative 4 e to the 2t. And our complementary would change 1, negative 4 e to the 2t. Now we can come back down here. Write our general solution as C1 times 1, negative 4 e to the 2t plus C2, 1, 1 e to the 7t plus negative 2, 6 times t plus negative 4/7, 10/7. We will next be looking at variation of parameters. Now, for variation of parameters, we look at the complementary function, which was C1 phi1 plus C2 phi2 yada 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 plus Cn phi n. we can write this as C1, phi11, phi12, phi1n plus C2 I already screwed up to change these labels. Phi11, phi21 down to phi-n1, C2 then phi12, phi22 down to phi-n2 plus yada yada plus Cn times phi1n, phi2n down to phi-nn, which can be written as C1 phi11 plus C2 phi12 plus yada 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 plus Cn phi1n, right, so on and so forth. Then we'll have C1 phi-n1 plus C2 phi-n2 plus yada 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 plus Cn phi-nn. Now this vector here is actually a product. It's a product of a n by n matrix and a n by 1 matrix. So we can write it as phi, the complementary function, is equal to some matrix psi times a constant matrix C. Psi is equal to the matrix phi11, phi12, phi1n, all the way down to phi-n1, phi-n2, phi-nn. So psi is the matrix formed by letting each of the solution vectors be a column of the matrix. And this is called the fundamental matrix of the system. Now, there are two properties that we're going to be making use of. The first is that psi is non-singular. That means that an inverse does exist. The second one is that if psi is the fundamental matrix, of the system x prime equals ax, then psi prime will be equal to a times psi. Which makes sense because psi is a matrix formed from all the solution vectors. Now, just as we did when we were studying linear differential equations, using variation parameters, we guess a particular solution of the form psi times u. where u is the vector u1 of t, u2 of t down to un of t. The goal is then to find this u by product rule. Phi prime is psi times u prime plus psi prime times u. Plugging this into the non-homogeneous equation, we're going to get psi times u prime plus psi prime times u is equal to a times psi times u plus f. However, psi prime is a times psi. So replacing psi prime in here, we'll get psi u prime plus a times psi times u is equal to a times psi times u plus f. You can see that the a psi u's are going to drop out, so we're going to be left with psi u prime is equal to f, which means that u prime is equal to psi inverse times u. This means that u is equal to the integral of psi inverse times u dt. And so we can form our particular solution as psi times the integral of psi inverse times u dt. I'm sorry, I don't know where that u came from. These should all be f's. So this is our particular solution. So let's go ahead and use variation of parameters to solve the system. X prime is equal to -3, 1, 2, -4 times x plus 3t e to the -t. Determinant of lambda I minus a. So we get determinant of lambda plus 3, -1, -2, lambda plus 4, which is lambda squared plus 7 lambda plus 10. So we get lambda is equal to -5 and lambda is equal to -2 as our eigenvalues. For lambda equals -5, we have the 2 by 2, -2, -1, -2, -1, which will row reduce to 1, a half, 0, 0. So we have the system x1 is equal to -a half x2. By choosing x2 to be -2, we can get the eigenvector 1, -2. And so we get our first solution vector to be 1, -2 e to the -5t. For the eigenvalue -2, we get the 2 by 2 matrix, 1, -1, -2, 2. So this will row reduce to 1, -1, 0, 0, which gives us x1 is equal to x2. So by choosing x2 to be 1, we get our second eigenvector as 1, 1. So our second solution vector is 1, 1, e to the negative 2t. So our complementary function, or our complementary vector, is c1 times 1, negative 2, e to the minus 5t, plus c2 times 1, 1, e to the negative 2t. Our fundamental matrix psi is thus a 2 by 2 matrix, e to the minus 5t, e to the minus 2t, negative 2 e to the minus 5t, and e to the negative 2t. This gives us the inverse as a third e to the 5t, negative a third e to the 5t, 2/3 e to the 2t, and a third e to the 2t. So, the particular solution is psi times the integral of psi inverse times f dt, which is a 2-vector, 6 times the quantity 20t minus 9 plus 25e to the negative t all over 100, and 3 times the quantity 10t minus 7 plus 25e to the negative t all over 50. We rewrite this 6/5 t minus 27 over 50 plus 1/4 e to the negative t, and then 3/5 t minus 21 over 50 plus 1/2 e to the negative t. Therefore, our general solution, c1, 1, negative 2, e to the negative 5t plus c2, 1, 1, e to the negative 2t plus 6/5, 3/5 t plus negative 27/50, negative 21/50 plus 1/4, 1/2 e to the negative t. That concludes this lesson. I hope you've learned something, and we'll see you in the next one.